Okay. So what we are going to talk about today will be, will be on the first thing I'd like to talk about is the law of large number. So why we are going to talk about that? Because we'll use this to talk about a concept in information theory known as typical sequences, and we'll need that to. Oh, is there someone here? We'll need that to explain the typical sequences. So basically, what the law of large number what it is basically just saying that if we have some a sequence of random variables at x1, x2, and so on, up to xn, and assuming this all IID, so IID. So again, IID means that it's identical, and independently distributed. So in the sense each of them have the same distribution, and also all of them are independent of each other. So basically, the law of large number just describes something really obvious. Basically, it's saying that if I have this random variable x1, a sequence of random variables, you can think of this sequence of random variable is drawing from the source, right? This source is same some mechanism will spell out some random variables. For example, I flip a coin, and each time flipping the coin is independent, and also it's the same coin, it's the same distribution. Then for this sequence of random variables, if I for each of the random variable, I go for a function f, any kind of function that map, for example, f xi to fxi, let's say. Then basically, the statement of law of large number is just saying that if we consider the average of this sequence, this empirical average, not that sequence, I'm sorry, the empirical average of the functional output of that sequence, that means that if I take fxi from I equal to, let's say, 1 to, let's say, n, and I take a average value of that. So, and this average will converge to the expectation of fx. Or actually, I can write, for example, I will just simply write these two. Maybe I will just simply write that they are equal if I allow n's go to infinity, something like that. So this is the law of large number, and actually the way we are stating this is the so-called strong law of large number. Instead, I will show you a weak law of large number that is basically saying that instead of this is exactly equal to that, you can claim that the probability that is deviating from this value, basically, if I take the average of that sequence, or the output of the sequence, from the expected value, and we want to see how much these two deviate. So basically, we say the probability that this is bigger than any kind of positive value a. So here a is positive. This probability will be less than equal to the variance of fx over n a squared. So as you can see, if I take n goes to infinity, then this will go to 0, right? So therefore, this probability will go to 0. and this is basically, okay, this is the strong version, strong law. So this is like a weak law of large number. So we'll spend a little bit time showing this weak law of large number. Let's see like if any, okay. So so basically any question with the setup, like it's extremely simple. It's just saying that like if I have a random source and then I sample some random variable from that source, and of course all these random variables will be identically distributed, and also I will assume that they are independent to each other, and then for each of these output I can map with some function f into fxi, and I try to find the average. Of course this function like f here, actually this is not a very kind of correct like mathematical notation. Probably I should write like that, like something like x into, yeah, oh actually I think it's, yeah, I don't know how, I forgot how to write it kind of like more formally, but anyway, so this will be a function, of course, like it should map to, yeah, I should say like this should map to the real space, right? Otherwise I cannot, if this is not a numerical value, I cannot take the average. So of course I can be complex space, basically it will be the same. So like map to like some real space, I can take the average, and then this average, the empirical average, basically I just take x1, x2 up to xn and take the average, empirical average. The average will be the same as the expectation, basically, as n goes to infinity. And of course like this is exactly like why we do polling, right? For example, like if when we do some polling on like some opinion in the society, like we just sample some people, right? Maybe 1,000 people, and what we expect is like what you sample from that population will have the same kind of distribution as like the distribution of the entire society or so on. So therefore like that kind of like what your sample average will be the same as the true expected value that you really want. So let's look at a proof of this like weak law of large number. So we'll go through several intermediate steps for that one. First we will explain, kind of like introduce a lemma we call the Markov Inequality. So the Markov Inequality is like the following. So we have the probability of like some random variable x, where x has to be positive. So it's like some positive random variables, and for this random variable like bigger than b, will have the probability is less than the expectation of x over b. So this is like the Markov Inequality, and you can prove that pretty easily. Basically just give the proof for here. So we can basically write x as two different cases. Basically I want to say like x is larger than b, and also the case when x is less than b. So I'm basically doing nothing, right? This is a kind of indicator function. Basically when the argument here is satisfied, then it's
there is minus x there?
No, this is multiplied by x here. Yeah. Yeah, maybe I just write like that. So this is like an indicator function saying that like if the argument here is satisfied, then this is equal to 1, otherwise it will be 0, right? So therefore like this statement is basically just didn't say anything, right? Just split x into two cases. Like it's bigger than b and less than b, and of course like this will be just identical, right? Because either like if it's x is bigger than or equal to b, bigger than or equal to b, then it will be like this will be 1, this will be 0, then it's like x is equal to 1 times x plus 0 times x, right? And if like the otherwise, then we also have like this will be 0, this will be 1. So now, but then like we can we can write this to be bigger than equal to ix bigger than b times b, right? Because x is bigger than b, right? So it's bigger than that. I can write like that, right? And of course I can even write, because it's x positive, I can even omit this term, right? So therefore I have x is bigger than I, x bigger than equal to b of b, right? But then if I take expectation value, basically expectation on both sides, left hand side and right hand side, so then my left hand side will be simply expectation of x, my right hand side will be like expectation, this thing here, this is a constant, I can put it out and say b I x bigger than equal to b. And what is this basically? Or like I should say, like, what is this here? What? No. We are not talking. Oh, I'm sorry. Like, let me write this I here. I is not mutual information. It's just an indicator function. Not the bigger. This is basically like I is x bigger than equal to b, means that like it's 1 or 0 if x is actually bigger than equal to b. Otherwise, so basically I some kind of argument something is 1 if the argument is satisfied. For example, I argument 0 if argument satisfied, or if otherwise it's equal to 0. Yes. So then, like, what is this? Like this, as you can see here, this is actually nothing, but it's just probability x is bigger than equal to b, right? You think of like
probability is mean expectation.
No, the expectation, the indicator x equal to b, larger than equal to b, is actually just the I don't think this is necessary. Anyway, hello. Trying to call. So this okay. Yes, what I'm saying, like, this will be actually just equal to probability x bigger than equal to b, right? Because actually you can think of expectation indicator, some argument here, like some argument here, is actually just equal to the probability of the argument, right? Because it is essentially what it's doing is just saying that I will be counting the case that argument is satisfied. I'm set to 1. For all the other cases, I'm set it to 0. This is exactly like how we kind of like evaluate probability, right? Probability, right?
Yeah, that's
so
right.
yeah. So then then we have this. So therefore, this is just equal b times probability of x. So therefore, it's just basically this one here. So that's the Markov inequality. And then this is just the first step. Then let's introduce another intermediate step known as the Chebyshev inequality. So the Chebyshev inequality is saying that the probability of some random variable y, the probability that like this is kind of like how far is away from the mean. If the deviation or the difference is bigger than equal to some positive number a, so this is kind of positive, then this probability is basically less than the variance of y over a squared. So basically this is quite intuitive, right? I mean, in the sense that you expect like when this is kind of far away, I mean, not exactly intuitive in the sense of how extract, I mean the exact statement here, but I'm saying like when it's kind of like farther away from the, for example, if the variance is bigger, then the probability that can be farther away from some A here will be larger, right? Otherwise, and also like if this A is kind of bigger, wider away, then the probability will be like smaller also, right? So the form is kind of like reasonable, even though like we need a proof for the exact why so for the exact form here. So let's go through again like a quick proof for that. Like so, we'll just prove this using the Markov inequality. So how we are going to use the Markov inequality is like you see the Markov inequality is like that, right? So we have this something like that. X has to be positive and something like that. So what we can do is basically we need to introduce some positive random variables. So one choice here, okay, it turns out it will be working is like we just let x is equal to the square difference of y and the expected value of y. So if we take x is equal to that, then like we can just use the Markov inequality, right? Then basically the Markov inequality saying, let's shrink it, then it's easier to see, saying that the probability of y, x is basically y minus expectation y squared, right, is bigger than equal to b for some b is less than the expected value of y is basically x is basically y minus expected y square. So you already see the variance here over b. Then of course you immediately see that like this is actually just equal to, if we let b equal to let's see a square, let's say is that b equal to a square, then this is a probability of y minus expectation y square bigger than a square, and of course this is just equal to the probability of y minus e y, the absolute value is bigger than a, right? So then again like we have this b is equal to a square, and this of course this is just variance of y here. So therefore like we have the proof of Chebyshev inequality immediately. Now I think we are basically ready for the proof for the weak law of large number. So again, the weak law of large number is like this. Let me copy it to the next page here. Have a new. This is the weak law of large number that this is actually the this is a weak law of large number. So this
That's come from Chebyshev inequality.
yes, we're going to prove this like using the Chebyshev inequality. And remember the Chebyshev inequality is a probability y minus expectation of y bigger than equal to a is less than variance of like y over a squared. Actually, you already see the form is quite similar. So now what we need to do obviously is like we just need to set this to be y, right, basically, more or less. So let's set y is equal to this guy here. So in the sense that y is equal to this guy. So therefore, if we try to compute the variance of y, what is that?
Variance.
We set. Variance of
Why actually fx?
Yeah, maybe we should put y to f. Let's wait a sec. Oh, maybe I should call fxi as yi, and they are kind of identically distributed. Now let's look at the no, actually wait, actually that's okay. Let me do this again. So, but let me write yeah, I think it's okay. Let me call this y. But then what's variance of y? Let's see. Right, variance of y is equal to 1 over n squared. Wait a sec. Let me do it one step at a time. 1 over n summation I equal to 1 to n fxi. So let's say I just write like that. Right. Now now this is equal to this I think if you first time see this, you have to be very careful. What is this like? I mean, like, I should ask this, like, variance of a w. Let's say this is a random variables. Will be, you expect would be like some kind of variance of w, right?
A
Times
A.
No, it's not times a actually. It should be times a squared. Because you remember, like, variance is actually like expectation, like something square, right? So when you have a constant here, basically you have, I'm not going to show that, but this square, when you pull it out, actually will become a square here. So therefore, like, and okay, this is like variance of aw is equal to a square variance of w. And also, how about what is variance of w1 plus w2?
Variance w plus variance w2.
Yes. Actually, I should be careful here also. I can do this only when these guys are actually independent, or like let's say independent. Like if it's uncorrelated, probably uncorrelated is okay as well, because when you have uncorrelated, it means w1 w2 will be expectation w1 times expectation w2, assuming zero mean. So, okay, let me be since I'm already writing this, like, maybe I just be very careful. What I'm saying, like, what's variance w1 plus w2 will be like expected value of like w1 plus w2 minus mean w1 mean w2 square, right? And then, like, okay, and this I can expand that into like w1 minus w1 bar square plus 2 expected value w1 minus w1 bar, w2 minus w2 bar plus expected value w2 minus w2 bar, right? Square. W2 bar and w1 bar is basically the mean, right? Here is the mean. So this is just like I'm basically just doing a expansion of this square, and then because the expectation of is linear, so I can just do expectation for each of the terms here. And then like if we assume that like this is equal to 0. Actually, this is equal to 0 is the definition that, like, W1 and W2 are uncorrelated, then this will be equal to 0. And actually, if it's independent, like if W1 is independent of W2, it automatically kind of like imply that it will be uncorrelated. So therefore, it will be equal to that, and of course, this is variance W1 plus variance W2. So basically, if you have x1, x2, all these sequences are independent, then you expect the output of those, f something, fx1, fx2 will be independent of each other as well. So therefore, like this become like, first will become n square variance of this some stuff, right? Yes? Yes? You have a question? Oh, okay. Benny, somehow like you're still here, like maybe it's okay. Let me mute this. Okay. So and then like from here, if we can assume like basically if xi, all the xi are independent, therefore fxi are independent of each other, then it will become like n square sum of like variance of fxi, right?
Yeah, that's right.
Yeah. And also like because we assume they are identically distributed, like all of them have the same distribution, we can just write like fx instead, like variance of fx. So the index doesn't matter, the statistics are the same. So therefore you have n of them, like so you have n of them, but over n squared here. So you get like variance fx over n here. Then you just substitute this.
Over n quadrat, over n squared.
Yes, we have n squared here, if you remember here. Right? When variance of AW is equal to A squared variance W.
Yes, so there n squared.
Oh yeah, but got cancelled, like you have n of them here. That's a sum, right? Each of them the same, so you have n.
Oh, I see.
Yeah, so then you cancel one of the n here. And then therefore we are basically here, so we just use the Shabby-Shaff inequality here. So then variance of y is y minus the and what is the expected value of this y here? Expected value of 1 over n sum over f xi I equal 1 to n will be simply like, because they are identical, so I can just pull the expectation inside the summation. Yes, yes, they are the same. Yes, exactly.
Yeah,
So therefore, like this is just expectation fx, and again, like you have n of them, right? But this time, like you don't have n squared in the denominator, so you got n at the numerator and denominator cancel each other, so you just have expectation fx left. So now we have this here. Okay, again, like this is we call it y here. So then we have basically y minus expected value of y is just expected fx bigger than equal to a is less than equal to the variance of y, and we show that the variance of y is just variance of fx over n, right? This is variance of y over a squared. So then we just substitute everything into the Shabby-Shaff inequality. Then we have the
So for the y, where does it come from?
here where
This one?
expected value of y.
Yeah.
Oh, okay. This is this. Okay, this is the Shabby-Shaff inequality.
Oh, no, it's equal to that.
Oh, this is like which one, like bigger than equal to a?
This one is the same to this one.
Oh yeah, this is same to this one, because of here, right?
Oh, that's why.
Yes. So, so this is the weak law of large number, and now we will start using the weak law of large number to explain. Actually, you can use a strong law as well to explain the very one kind of like core idea in information theory. Like very simple idea is like you have so-called typical sequence. You have some discrete memoryless source. So this is discrete memoryless source. So you sample from this discrete memoryless source to get like x1, x2, and so on, xn. So of course the output from this discrete memoryless source will be IID. So it will be same kind of sequence we kind of described in the law of large number. Now we say that for the law of large number, like if we look at the empirical average of some function of this x, let's say I have f xi, we take the average, empirical average of them, let's use began here, will be equal to the expected value if n goes to infinity, right? So this is just the law of large number. Now,
From where then?
oh, this is the law of large number.
That's not that's below above. That's
No. Okay. I mean this whole because of the law of large number. You can ignore this. I mean, okay. This is kind of confusing you. Then you can ignore this. It's just I'm just saying like you have this just discussed earlier, right? This is by law of large number we have.
Oh, above earlier.
Yes, from earlier that we take a function of this output of this sequence, or like take a function of this sequence and take the average of them, will be just equal to the expected of that function of x, say. Yeah. Now let's take the function as following. Let's have like function of x. Let's define this fx as log 1 over px. So this is like the probability here, right? Then what we have is basically I have log 1 over p x I from 1 to n over n kind of like will converge to the expectation of log 1 over px, right? But what is this value here?
That's entropy.
Yes, that's the entropy, right? That's just the entropy. So basically, like if you have the function, kind of like you have you're drawing a sequence somewhat from a discrete memoryless source, and then like you just map each of the output x1, x2, and so on into like this log 1 over pxi, and then you take the average. This always gives you the expectation. This is a kind of series, right? In the sense that it's kind of obvious, but let's see. But the left-hand side here, we can also write this as let's see. I have this sum of log, right? Sum of log can be viewed as the log product of this argument, right? Right. I have log AB is equal to just log A plus log B, and so on. So and then like let's see, and then this. Okay, I have product of this, but I can also write this as a log 1 over product. Yes.
We know that the entropy is Px times log 1 per Px. So where's the Px about earlier? Where there is a take out.
You mean this side or this side? Like on left?
That if we this is also equal to Px.
Oh yes, yes.
Log 1 Px. Yeah. This minus.
Yes.
So where is this Px actually gone from here? Is it actually should be same with this?
No, but you see that this is like saying that for x is for example, if you look think of like an example here, if so your question is like this side doesn't seem to match with this side, right? But you think of like a realistic example, like what are you summing like on the right hand side or the left hand side? Like for the left hand side, you're summing for each of the samples that you draw from the source, right? For example, like I just think of an example of flipping a coin here. Then the left hand side, like xi, for example, my x can be like head, tail, and so on. Maybe I use head, tail as like 0 and 1, right? Then I will have value like 0 and 1 and so on, this kind of values on the side. And the probability of this and so on, I have mapping. So I'm summing over for from 1 to n, right? For the entire sequence. But this one, I'm only summing the two values, right? Only 0 and 1, right?
Yes.
And then like this, what should I say? When you, let me put it this way, maybe like it's clear, right? Like that. So let me ignore this guy here, just think of like fx I sum over I equal to 1 to n, 1 over n, and also like px log p, not px and fx. Something like that, right? Yeah, this will converge to this way, basically law of large number is saying. Yeah. And so, but this is really logical if you think of that. What you're doing here is like, you're doing kind of like, when you're jumping from here to here, it's like you actually try to estimate the distribution of px from this one here. For example, like let's say I'm just kind of I need more. Let's say I'm just like floating dice here. Then I have like on the one hand side, or like okay, let's do con. So I have like 0 and 1 and so on, right? 0 and 1. And on the left hand side, I'm summing up this thing is like I equal to 1, and then like up to this n here, right?
Yes.
And then I have like, let's say I just take the average of them, let's say, and just take, I'll call it xi. Let's even ignore the f there. And then this is like x px sum over x, right?
That's right.
But here is sum over x is basically sum over just 0 and 1, right?
Yes, sir.
And here what I have doing this xi, for example, like if you look at here, I can group into two kind of sets here. I equal to
1,
1, 3, 4, 6. You can see here like this is the set that is equal to 1, or this is like the set that like I such that xi is equal to 1, let's say, right? In that case, it will be like xi is just equal to 1, right? And then like plus I in the set like xi is equal to 0, right? And this is 0, right?
That's right.
And then 1 over n, right?
Yeah, that's
Or in general, like I can be like this is basically I equal to A, for example, like this is equal to B and times A and B, right? Or maybe like equal to A1 times A1, and then like this is equal to A2 times A2, let's say. But then like what you are doing here, this A1 you can pull it out, right? Because it's a constant with respect to this guy here. Then you sum over I xi equal to A1 over n. So this is just approximating Px equal to A1, right?
Yeah, that's right.
Yeah. And this is approximating, like this will be again similar to A2. Then I have something similar. I equal to A2 would be like Px equal to A2, right?
Yeah, that's right.
So that's the things that coming from here, right? That's the P, right?
Oh, and then x.
Yeah, X is here, right?
X is A.
Yeah.
Oh, I see.
Yeah.
And then where's the log in that?
But there's no log here. Like the log here, which one log? Log is on the previous page, right? You mean the log here?
Yes. And then this log is A in here.
The log here is just like if we take the function f as log only,
Oh,
right?
yeah.
It's nothing special. Like we take the function as like log 1 over p. That's our function, but that's nothing really special. You can think of that just f, right? But if you take the function f is equal to log 1 over p, then we'll just have this is equal to hx, right?
Oh,
Yes. So and then let's go back to here. Like right hand side is hx, but then left hand side is equal to this guy here. And then as I said, like I can have like some log something is equal to log product of something, right? Log a plus log b is equal to like log ab, right? Something like. So then like, and then this will become this, but then like this guy here is just equal to px, right? Px as the probability of the entire sequence, right? So therefore, basically what we have is like log 1 over px, the sequence over n will approach hx. Or we can kind of like flip the terms. If we, okay, I need more space. If we do exponential on both sides, basically we multiply n on both sides. And then we do exponential on both sides. Or maybe we do an inverse first. Let's see. Okay, we can put a minus sign first. Then basically px will approach exponential minus nhx, right? Something like that, right? Basically, I just say put a minus sign on both sides. Then like this log 1 over px become log px, and then n multiply on the other side I have like minus nhx. The exponential both sides, and I have px approach exponential on like nhx. So it's saying that like, okay, if I have a sequence, I'm drawing from that sequence, and the sequence, if I look at the probability of that sequence, is always like approaching this value is exponential minus log nhx. There's sometimes like there's a name for that, like in some of the textbook, for some of the textbook from Cofer and Thomas, is known as the asymptotic equipartition. So it's equipartition, right? Because all the sequence, if you think of like kind of like the probability space of all the sequence drawn from this source here, then you can have like, for example, like this is the probability space. I just draw like this is the probability. So okay, in the sense I drawing this, I don't know what kind of it may be weird, but what I mean is that like you could think of like this part is basically the probability of a particular sequence, I say, where the sequence lie into, and and the size of that correspond to the probability of that sequence. And so therefore, like the entire space here will sum up to 1. Now, and what I'm saying is that like basically like, each of the sequence will have the same probability, right? The same probability as this one, as n goes to infinity. And also, like the probability will be exactly equal to this guy. Actually, it's like have exactly this formula, exponential minus n matrix.
So actually, that is the joint probability. This is a joint probability for all of the probability and that.
Yes, the joint probability of a sequence, or like, yeah, the joint probability of like the samples in the sequence, or you can just simply think of like the probability of a sequence, right? You draw the sequence from this guy here, and the probability that like you have this sequence, for example, like 1110001, something like is the sequence drawn from here. Exactly take this value 111011, something like that. The probability will be just this. Yeah.
And then the HH in here is entropy for every particle in here.
Yeah, the entropy. Yeah, this is the entropy for the.
For one particle.
Yes, for one sample, like.
One sample.
Yes. Or like, or I should say like entropy of that source, or you can. So basically, this is a px log px. Yeah. Just log. Yes. Yeah. So px is basically a distribution of that source. Yeah, or maybe I use 2 to something like if the unit, if this is bit here. So, but anyway. Yeah, that's n. Yeah, n here. Yeah. And so with this, basically, you can define something known as the typical sequences. Typical sequence. So typical sequence is nothing, just because we already claimed that like pxn or like a sequence will be the sequence of length n will be have the probability approximately 2 to the minus n matrix, right? So basically we say like any sequence have probability approximately this guy will say is typical sequence. So to define it in a more kind of concrete sense, we will define a set of typical sequence. This is set of typical.
Where's the 2 come
Huh?
from? 2.
Or 2, yeah. We use exponential like earlier, but as you remember, like it depends on like what kind of unit we use for hx, right?
Oh, yeah.
Yeah. Here, if I assume like hx in the unit of bits, then it would be like 2. Then I write exponential earlier, but then like I think it's better I just use like bits as unit, so I put 2 here. Yeah. So it's a 2 to the minus n matrix. So so back to here, like the set of typical sequences is just define the set of sequences, length n sequences, that the probability will be just close to this guy here. So let me write this. So by the way, this notation I'm using here is like just a shorthand notation that this is equal to x1, x2 up to xn, something like sequence of that. And it's less than equal to 2 to minus n hx minus epsilon, and bigger than equal to 2 to the minus n hx plus epsilon. So it's just a definition of this a set of typical sequences. So the point, the basically the argument here is that like we can put this is like similar to calculus, this kind of epsilon and kind of delta n arguments. So no matter what finite s we define, finite epsilon we define. So as long as I for any finite epsilon, so that means that any epsilon is bigger than 0. So there will be some n. I can find some n such that basically like all the sequences will be kind of typical. Right? So I'm not writing something very kind of extremely rigorous here, but here it would be something like if we really want to elaborate, it would be like the probability that like you draw a sequence that is not typical will be very, very small as long as n is sufficiently large. And here we can pick any epsilon, it doesn't matter. And also, like by the way, like because with this kind of assumption, because all the sequences have more or less the same probability, right? And also, like all these sequences are basically typical. That means that like if I sum up all the sequences, the probability of all the sequences, all these typical sequences, should be equal to 1, right? Or something like I can write sum over px, like for x in the typical set here. This should be, oops. This should be close to 1, right? Something like pretty close to 1. Because everything is typical, right? I'm summing up the probability of x. Of course, this should be less than 1, but this should be like sufficiently close to 1. Or like I may yes.
What is the correlation between typical sequence and set of typical sequence? Mean that that's probability, and this will be less than this one probability, and this is n. So this is
yes.
This and this is that's under that.
Yeah.
So actually, this is x given to this one. X n given this probability.
No. Oh, okay. Do you okay? Are you familiar with this kind of set notation? Like when we write, like for example, like a set like x, for example, like fx bigger than equal to b a, let's say. Are you familiar with this kind of notation? This is just a notation for the set. It's saying that like this is a set for all the x that satisfy this condition. Yeah. So this is just a set notation. Is saying okay, this is like the set for all the sequences that satisfy this condition. Basically, the probability of this sequence is within this range. So it's basically it's like something. That was the osmol or like tautology. So. We just define something is obvious.
Yeah, that is
so
about the limitation in the left and the limitation in the right, and that's
so
around of that.
Because we know that like for any sequences from that drawing from that source will be kind of like within this range here. So therefore, like every sequences we draw will be more or less typical. But that's why we call it typical, right?
Meanwhile, you know that before that we have that, but in here there is x power n. So and there is
Oh, okay. I'm sorry. Like, I'm mixing these two notation. These two are identical. So I write this x bar is meaning a sequence of x1, but when it's the same as xn, but essentially xn is like also a shorthand notation. This actually these two notation is kind of identical. So but sometimes people write like this just being lazy is easier, and it's cleaner, looks like. But this two is just the same. Yeah, this is just referring to the same thing. But here we also specify the length of n, basically, say from x1 up to xn. Here it's just a vector of xy, just, yeah. Yeah.
So that is just notation.
Yeah, just notation. These two are the same. So, but I just, yeah, make sure you understand the concept here. The concept here is very simple. Basically, like everything drawn because of law of large number, every sequences drawn from that source will have the probability come close to 2 to minus nhx. So therefore, we just define something called typical sequences as long as that probability, the probability of the sequence is not too far from that probability 2 to minus nhx. So given that, then any sequence will be kind of like typical. Yeah. So because any sequence is kind of typical in this sense, then if you sum over all this probability, of course you pick here I'm just summing the probability of like all the typical sequences, right? And this will be, of course, will be less than equal to 1, because it's like you can have like sequence that is not typical, but the sequence that are not typical will be very tiny. So we may write something like is equal to 1 minus delta or something like, and this delta will be pretty small. The delta will be goes to 0 as n go to infinity also as well. So and because of that, I'm also like, if we write like this, px will have probability approximately 2 to minus nhx, right?
Yeah, that's right.
So and you have that is like basically you sum over. So therefore, like this probability can pull it out, and you have how many of these? You have like the total number of typical sequence, right? Let me denote at that. That's the number of typical sequences. That's the size of the set. So, and so therefore, like the size of the set, or like the number of typical sequences, will be just approximately 2 to nhx, right? Times 1 minus delta. Or like if you ignore the delta, it will be just approximately 2 to nhx. So you have like approximately 2 to nhx, so many typical sequences, and also like all of them will have the probability close to like 2 to minus nhx. Oh, this is 1 minus. 1 minus delta. So delta is like supposedly pretty small as well.
Yeah, it's small.
Yes.
So that I can get it. Where is up from? So.
Oh, this is just the size, right? Because let me just go through this more precisely. Maybe then maybe it's clearer. So I have let's say I have let me rewrite this. Maybe I just copy paste this faster. Copy this guy here and copy to here. So again, I have basically the sum of probability is just 1 minus delta, right?
Yes,
Delta is kind of small as n goes to infinity. It's actually just go to 0. Now, and then and we have, remember the definition of the typical sequences, simply satisfying px px is 2 to the minus n hx plus epsilon. Yeah, that's the definition, right? If it's typical, then the probability will be like will be bigger than this, way. It's within that range, bigger than this and less than minus epsilon, like the other side, right?
Yes, that's right.
So then this guy does not depend on x, right? This is just a constant, right?
Yes, right.
Right. So I can pull this guy out. So therefore I have like 2 to minus n hx plus epsilon, then sum over x a s n times 1, right?
That's right.
But what is this doing? It's just counting how many sequences is in this typical sequence, right? Typical self-typical sequence, right?
That's right.
So we just denote this as the size of the set, basically. This is a common notation, right? You have a set S, we say the size of the set is just like this. So the size of that set is just, so therefore I have, this is basically the size of that set. So will be equal to 1, that's less than equal to 1 minus delta here. 1 minus delta is, yeah. And so therefore I have the size of the set here is less than equal to 1 minus delta times 2 to the n hx plus epsilon. Wait a sec. Something looks not right. Oh, where's that? Yeah, actually it's okay. Yeah, that's fine. But wait. Yeah, that's fine actually. But typically we don't even need that. If we like to keep that, it's okay. But we actually only need that for the other inequality. So if I have x. Okay, why I'm saying I'm don't need to keep that, because this is less than equal to 2 to the n hx plus epsilon, right? Delta is like positive. 1 minus delta is less than 1. So yeah. So I just want to follow what I have in the notes here. So now and I can also have the other side, right? I can have like px. Again, I can copy the same thing here, but now I mean the same thing here. But I can have the other side, right? I can have say that this is bigger than equal to px, right? But this is minus.
Yeah.
Yeah, this is just again the definition of the. And then like we will have, again I do this, I can pull it out. Then I will have like 2 to the minus n hx minus epsilon a epsilon x, right, is bigger than or equal to 1 minus delta, or this a epsilon x is bigger than 1 minus delta times 2 to the n h x minus epsilon. Yeah. So therefore, like combined with this, I will have this ax have a range like that.
That also could be delayed then.
1 to 1, huh?
This one could be delayed also.
No, this one I cannot achieve because I have the inequality on this side, right? So this cannot be bigger than 1 minus delta is not bigger than 1, right? The other side I can remove that.
1 minus delta.
Yeah.
Is now 1 bigger than 1.
Yeah.
Oh,
Yeah. Delta is like positive, right?
Yeah.
So yes. So I have to keep this side on the other side. So therefore therefore we find that, like, okay, what's the size of typical sequences, the set of typical sequences, or the number of typical sequences will be more or less 2 to nhx, basically. You can put a range here, but delta is pretty small and epsilon is pretty small, so approximately there will be 2 to nhx, so many of them. And let's see. And that's it. Right? So that's the asymptotic equal partition.
So that is typical. So what is the physical meaning of this?
Yeah, you see some usage for that. Like it's actually means it's a way to do some proof, and using this kind of like argument using typical sequences. Again, let me maybe give one example first. Maybe it can become a little bit more clear. So let's say we have like again like we just flip coins, like flip coin as we use this example again and again. But let's say this time the coin is biased, so probability of head is 0.3. Now just think of like we flip the coin 1,000 times. So what we discussed so far basically saying that like you should have the probability of that sequence you drawn from that will be approximately 2 to the minus nhx, right? Let's see. And I'm actually how should I put it? Actually, this is nothing, but it's basically saying that the sequence that you draw 1,000 times, flipping this coin 1,000 times, given the coin is biased with a probability of head is 0.3, then you expect that you will get about 300 head and 700 tails.
Yes.
It will be about getting that. You basically won't get like something like 100 head and then like 900 tail.
900.
I mean, like like you will basically like all the time you will get something like that instead of this one. We can try to verify that. For example, like what's the probability of getting this? Will be like let's call this like p p hat and p tail, just for convenience. So the probability will be p hat 300 times, right? And p tail like 700 times. That's the probability to get a sequence like that. And but we can also like write this as p hat. This is like p hat over n, where n here is 1,000, right? And p tail over n, right? And then I can write this as, let's see if I can put log as a, I can write exponential to log this handwriting is too bad.
That's ID.
Uh-huh.
That's identical. Four times.
Yes, they are. Yeah, they are identically distributed. Yeah, they are ID. And when I let me just try to continue. This one here, it's basically just log pH over n, right? pH.
Yes.
Yes. And let's see. And plus pt log pt, right?
But where it come from?
See if I make I'm thinking that did I make some okay, I'm sorry, like I make mistakes, that's why it looks so weird. Let me get back. Times n should be, right? mph and pt mpt. Yeah, yeah. N is 1,000, something like that. So then, yeah, then that looks much better, right? Then I can write 2 log 2. This is just like, okay, I'm taking a log and then to exponential, it just cancel one another. And pH and pH. PT and PT, and this is equal to 2 log MPH log pH plus MPT log PT. Yeah, okay, I almost got that. Okay, yes, that's correct. So I have minus n minus pH log pH PT log, yeah, minus PT log PT. This is just the entropy, right?
Yes.
So that's okay. Go through a loop here. We just go back like what the intuition is. So if you have a sequence drawing from that, you expect like 300 head and 700 tail, right? And you look at the probability, it should, in this I should have like 2 to the minus n matrix, right? So of course it's just going back to like just an example.
But my probability in here should be power 300. So it should be power.
Oh, 7. No. I mean like if we pick a sequence to have like 300 and 700, because we expect that like if the cone is biased, if we fold that 1,000 times, then we expect that will be approximately 300 and 700. So many of them, or approximately so many of them, right?
Oh yeah,
So-
that's right. Yeah.
Yes.
So for every sequence is that's P, PH, 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 PH. Yes.
Yeah, that would be like
300.
about 300 of them, and then like 700 and
Oh, okay.
yes. Okay. Yeah, okay, I guess I will take a break for again like 15 minutes. Maybe come back like 35, then like 4:35, then we'll continue. Yes.
Yeah.